Welcome back to our second lecture on textile finishing. Let us see what we had done in the last lecture. We had learnt that there are several unit operations in textile chemical processing, starting with singeing, desizing, dyeing, etc. Finishing is one of the final unit operation. This operation adds tremendous value to the product. We also learned normally what could be the objectives of finishing. One of the interesting objectives is that it does enhance the aesthetics. Also, another important role and objective of finishing is to improve the functional performance of textiles. So, to achieve this, there are a number of finishing treatments which can be categorized into mechanical or chemical. The mechanical finishing processes would generally be dependent on the machine itself, while the chemical finishing processes would be more dependent on the chemical structure of the compound. Of course, as we said, that machines would always be required to do any finishing treatment, but the emphasis in a chemical finishing process is the chemistry of the chemical compound that has been used. In the mechanical, it is only the machine part which is the most important agent to affect the change in the functioning or aesthetics. Let us go further. So, today we will concentrate little more on wrinkle resistant finishes and learn a few things about it. What do we learn? We will first understand the need, why it happens and why we should do it. Other is, do we have some strategies to impart wrinkle resistance finishes and what are those strategies? And some relevant finishing agents also that can help this cause will also be discussed today. So, before we take up the topic, let us look at some of the fabrics, right. This is a fabric of cotton, right. This is a cotton fabric. At the moment it looks good, but if I press it, you can see the creases. You see the creases? They are more clear now. We started with a fabric which looked pretty plain, nice looking, and now suddenly it has so many creases. This so many creases you can clearly see. See that? Is it more clear now? Yeah. So, look at what happens to the cotton fabric the moment you compress it in your fist, bend it, crease it. The more you do it, the more creases you can see. I am sure you may not like to wear this type of a material or a garment for that matter. We look at another fabric which is this fabric, all right. This is a fabric which is woolen fabric, and if we try to do the same thing and see what happens, this is a fabric which does not have crease. I try to do similar thing and then look at this. It has less creases. Of course, I can still do more, it may see, but compare this fabric with what we saw on this. You see the difference? You see the difference? So, this is the difference that we were talking about, and that is why we may say we may like to have some kind of a treatment. Let us look at another fabric. This is polyester, which is the polyethylene terephthalate, and this, if we try to do the same operation here, there are some creases you can see, but look at this. That means some fabrics, because of the chemistry being different, this is wool, this is polyester, and let us see another fabric which is nylon fabric. It already has some creases because the way I handle it, but if we do further this, you may still find that the situation does not change much. All right. Look at this. So, the cotton among these is creasing, but the synthetic ones crease less. But let us look at another natural fabric, which is a silk based fabric. This fabric has not been degummed properly. Anyway, it has micro creases, you can see them, and if you do something like this, this also develops more creases than, let us say, a fabric which we first saw is the wool fabric. That means, based on the chemistry or maybe the treatment that we would like to give, some of these fabrics would crease more or less, and if they crease naturally more, what are we going to do about it? Right? This is what we may like to see. So, what have we learnt? That cotton creases the most. So, let us see why does this happen. Is there any relation with bending as crease formation? Why? Because we just took and crushed it, so there were more creases. So, possibly there may be a relation. One of the interesting thing is, whenever you bend anything, in this case maybe a fiber, so you will always get a compression zone and an extension zone. So, the outer side obviously is getting extended, inner portion of the bend is getting compressed, and therefore, there must be some strain and stresses getting developed in this region, because mechanically you are doing. When we try to squeeze something like this, obviously a bending is happening, and in this bending process some portion are getting on the outer side and therefore, they are getting extended, some which are inside this bending area are going to be compressed. Now, this is the way we believe every time we do this crush type of a thing or any other such process. Let us see, interestingly, what do we have? Let us say this is the paper, all right. This is a paper, and this paper I have bent, and therefore, there is an extension and there is a compression zone. All right. Now, this paper is a thin, from this side the thickness of the paper is less, this is there. Like for example, in this case you had external portion which you can see and the internal portion also which you can see. If I just leave this, it becomes still the same plain paper, there are no, it recovers. So, bending is okay, but after bending it recovers. So, it is a different property altogether. That means, we are interested in bending. Of course, whenever we do something, we sit down somewhere, some crease can be formed. What will be important is, does it come back? It is coming back, no creases. But if suppose I make the bend very sharp, now if I do this, now it does not recover that much, that crease has been formed. You see that crease now? The crease is formed now. You do it further, another crease is formed. And if you do like this, well, this is it. Now, it is not recovering. So, why does it crease and why does it recover? So, let us see a molecule like a cellulose which is in the cotton, also in the paper. So, you see that the cotton also creases, recovery is bad, the paper also creases, recovery is bad. So, we say, well, the both are made of cellulose, but that is one part only. Cellulose, you see this molecule, this is the repeat unit of the cellulose, which is called the cellulose unit. So, what it has is, it has got a primary hydroxyl group and secondary hydroxyl groups. So, we probably know already that the primary hydroxyl group reactivity will be higher than the secondary hydroxyl group reactivity. That is one part. But then what else? What else is that the molecules in the cellulosic fibers, other than the structure that we have seen, also make secondary bonds. What are those secondary bonds? The secondary bonds are hydrogen bonds. A large number of hydrogen bonds can be formed, because you have got so many hydroxyl groups, and these bonds are weak bonds, all right, they are weak bonds. So, what happens when they are weak bonds? During this process of crease formation, these bonds may break also. Why these hydrogen bonds are weak bonds? Because the energy required to break them is less. Let us say between the hydrogen bonds can be formed between the hydrogen of and oxygen like in water, hydroxyl group and oxygen like in water itself. And so, some of these things, although the energy level will vary, even hydrogen bond energy level will vary depending upon, sometimes they are called the strong hydrogen bonds or weak hydrogen bonds, but generally they are secondary and relatively weak. But in the cotton cellulosic fibers, the intensity of these bonds is very high. There are so many hydroxyl groups and there is so much of a possibility of making so many such bonds. And that is the reason why cellulose by itself is quite strong. The cotton fiber is pretty strong, although they are weak bonds, but if they are intensely available to do this, to share the load, and so the strength etc. are pretty high. However, in the case of bending, things can happen differently. We do have crystalline structures in the cellulosic fibers. The cellulosic fibers, as a cotton for example, has higher crystalline structure compared to viscose, which is less crystalline structure, but they are cellulosic fibers. So, what you see here is the possibility of formation of hydrogen bonds everywhere. So, between the thing which we have intermolecular hydrogen bonding and sometimes intramolecular hydrogen bonding also is possible. See that? So many possibilities of making hydrogen bond. The moment they are near each other, the molecule, some of this bonding can happen. So, as such the fibers are good. We do not have too much of a issue with the tensile property, particularly dry tenacity if we talk about. But we must remember these are secondary bonds and they are weak bonds. You see this structure which has got some bonds, which are these called cysteine, disulfide, disulfide bonds. Now, these bonds are covalently linked, the carbon to sulfur to sulfur to sulfur and sulfur to carbon, they are covalently linked. So, they are covalent bonds. Where do we see them? Where do we see them? We will see them in wool. Wool is a protein fiber. As we said last time also, that the molecules are also called polypeptides. So, peptide, that means the any kind of a protein is formed by various amino acids, which are essentially alpha amino acids. So, you get a polypeptide link, but interestingly a wool has other bonds also. It has hydrogen bond possibilities. As we mentioned, it has got the possibility of electrovalent bond at different pH levels. It has obviously a possibility of hydrophobic bonds. On top of it, it also molecule has helical structure. All of that make this material, after creasing, this material can recover. They make this material crease resistant. But silk, it has the possibility of all hydrogen bond formation, electrovalent bond formation, it has the possibility of hydrophobic bond formation, but has no possibility of having covalent bond. So, the chemical structure is different, the behavior is also different of different fibers. So, what is the interesting thing which is coming out? One is we are more interested in recovery from any wrinkles that have been formed. So, there is a term which is used which is called resiliency. Resiliency has two components, one is resistance to deformation, other is recovery from the deformation. Now, a textile fabric can resist, of course, but the forces like this are too harsh and too strong for it to resist, but it can recover. If it recovers, then we will find that the crease visibility becomes less, because it recovers from the crease. Crease can be formed because mechanical forces could be strong, but recovery is the one which we are going to be more concerned about. So, what was different in wool, silk and cotton? Intermolecular cross-linking. So, the fiber which is naturally covalently cross-linked is wool, right? If such type of a covalent cross-linking is not available, then what happens? Then we will not be able to recover, not as nicely. Remember, this paper is recovering from bending, but does not recover from sharp bending, because something must have changed. Why it was recovering? Why is it recovering? It is recovering because when we bend, some stresses are imparted, strain energy, because expansion and compression happens, is being stored. If the strain energy is being stored, then obviously by opening it releases the strain energy. We bend again, there is strain energy stored in this whole process. Here the molecules are getting to change their positions which they do not like, and so when you release the stress they come back. But when you do this, they are not able to recover, because at that point it is such kind of a sharp creasing. Something has happened. What is that something? Some of the intermolecular bonds have broken. The primary bond, which is a covalent bond of the main molecule, that does not change, that does not break by this process. What is broken is intermolecular bonding. That was in this case was a hydrogen bond, which is weak, and so you can break it, all right. But wool has covalent bonds, intermolecular covalent bonds. Therefore, this becomes an interesting part. If covalent bonds are available, then the strain energy gets stored, the bonds get stressed, but they do not break, and so if then the forces are released, they would like to recover by releasing that energy which has been stored during bending process. That is the way we look at it. So, that is our wool. If naturally these crosslinks are not available, then we have to create them. So, we have got a principle now. If we can create crosslinks, intermolecular crosslinks, then we would have an opportunity to see that the recovery is becoming better. Of course, resistance also will be increased, but we are more interested in recovery. So, what do we need? We need a cross-linking agent now. So, the chemistry of a compound also is equally important. There should be cross-linking agents which can react with the molecules of the fiber, whichever the molecule which we are interested in, to create covalent bonds. Now, if somebody would like to know, so we now have what we call as a cross-linking agent. This cross-linking agent we think will be able to cross-link some of the molecules and so when you bend such a molecule after it has been cross linked, it will be able to recover. So, by looking at this, what kind of agent would you want? Would you want a monofunctional agent? Monofunctional agent, that means there has got one functional group which can react. Is it good? May not be, because if this is the molecule, it reacts at one place, the other is dangling. If this happens, then we may not be able to get what we are interested in, because if we bend, this can slip. What we need therefore is not less than a bifunctional agent. So, we would not be able to do our job with a monofunctional agent. We would require minimum of a bifunctional agent, so that this has got two functional groups, which can react with neighboring molecules of the fiber and create a cross link. What about polyfunctional? Will they not form cross link? Of course, they will also form cross linking. The only thing which will normally happens is that if you use a polyfunctional agent, the network structure, 3-dimensional network structure can be formed. As far as resistance to bending is concerned, definitely it will be more resistant, and hopefully if everything is all right, it will recover also from the deformation, but it may change some of the properties which you may not like. For example, see this fabric, it is so soft. If this becomes stiff like this paper, you may not be able to wear. So, polyfunctional agents, cross-linking agents can create a 3-dimensional network which can make the fabric stiffer. So, unless and until you require stiffness, it may not be a good idea. So, generally people like to have bifunctional agents which may be the cross-linking, but polyfunctional can also cross-link. So far what we have done, you understood crease resistant finishing would be required and can be obtained by some cross-linking portion. So, initially what we should do is we look at the cellulose based systems, based fabrics. How do we do the cross-linking there? They are widely used also, and so it will be nice that we learn something about them before any other fiber. But before we go further, we must know how do you evaluate a crease recovery. This type of a situation, whatever has happened is good or bad, but how do we say this is, which one is worse than the other treated material, or after treatment how much it has improved? That we would like to understand. Only then we can say whether our performance has improved. So, also again remember, we are talking about recovery and not resistance. Resistance, as we said, it can resist, but if the external forces are strong, it has to bend. So, we do have a measure, we call it crease recovery angle measurement. So, you put a crease, and after putting a crease you see how much recovery takes place, and that measurement or the parameter which we measure is called the crease recovery angle. Sometimes it is also known as CRA, which is crease recovery angle, or WRA, which is wrinkle recovery angle. This is expressed as the sum of angles of recovery in warp and weft direction for a woven fabric. So, we have weft direction of woven fabric and weft warp direction. So, you measure separately the recovery and add them. And so, if we say recovery in the warp direction is this much, in the weft direction is this much, the total CRA would be a sum of these. If there are other fabrics, well, if it is a knitted fabric, you will talk about courses and veils. If it is non-woven, you can talk about machine direction and cross to the machine direction, and that is how you can measure and report the values. And what is the test? The test is you cut out some samples in a certain dimensions, here 2 inch by 1 inch dimension for example, and then bend them, fold them, put certain amount of weight for a certain time, for example 2 kilogram for a minute, and then remove the weight and measure the angle which has been recovered after removal of the weight, and obviously for a certain period, let us say here 1 minute. So, you load and remove the load. So, how it is done? So, you have a load, you bend it like this. So, this is the bend. So, it will be very sharp bend because you are putting the load. If you say 2 kg, it is a heavy load. So, there will be a sharp crease formed. And then if you remove the load, we expect this to keep rising, but important will be that if it starts rising, after some time you may find that the gravity is working against this rise, and so you will get a value which is different. So, how do we do the test? So, what people have designed is that you have a dial which obviously talks about angles. You have some clamp. In this clamp, this fabric, folded fabric, after removal load is put in the clamp, one end goes inside the clamp, the other is hanging freely. One end goes inside the clamp, the other end hangs freely, this is the center. And so, it will start recovering in this direction, the fabric edge will recover in this direction. In order, if it recovers more, then the gravity will start acting. To avoid that, you start rotating the dial in the opposite direction, and therefore, this clamp also, so that the hanging portion always remains vertical. So, there may be an edge, you keep matching the edge as it is rotating, so that the gravity effect can be taken care of. And so, after 1 minute you say how much recovery has taken place, and that will be your crease recovery angle in one direction, then the other direction, and then you add them up, will be total crease recovery angle. An equipment may approximately look like this, where you can see this is a clamp area and this is the freely hanging edge of the hanging portion of the fabric. And so, you ensure that this remains vertical, it remains vertical. So, that is how we measure the crease recovery angle. So, whenever you do a treatment, you would like to know whether we have improved the crease recovery performance or we have not. So, let us look at what we have learned till now. We have learnt why creases are formed, how can we overcome this deficiency, and how can we calculate crease recovery of a fabric, treated or untreated. Let us see how can we make the cellulose based fabrics wrinkle resistant. Wrinkle resistant finishing has to be done. We were talking about fiber and the chemistry. So, the textile is available in the fabric form, is available in the yarn form, is available in the fiber form. So, which product is what you think we should be applying these chemicals and getting through the cross linking process? Is the fiber or the yarn or the fabric, which one? So, as far as chemistry is concerned, you can do it on all of them, but people would like to work on fabrics. They are almost the products that we see. Fibers and yarn are the ones which have helped them to go. Ultimately, the reactions will happen in the fiber, within the fiber. The chemicals will be able to diffuse inside the fiber, whether you take yarn or a fabric. So, ultimately the fiber has to be modified, but the treatment may be done on a fabric, which is a better idea. Let us look at the cross linking agents. So, we did say that we would probably like to have generally a bifunctional agent. So, it is clear that we need to create cross links between the molecules, generally intermolecular cross links. Why? Because that is how these cross links are covalent. Because they are covalent, therefore, they will stretch by during bending, but will not break. And if they do not break, then we will be seeing that the recovery can take place. So, covalent bonding will be required, which are strong bonds, they do not break, and so we would be doing this. Now, let us look at cross linking agents. The cross linking agents can be, as we said, they should be bifunctional, but they may be broadly classified as some which are nitrogen based cross linking agents and they are non nitrogen based cross linking agents. That is how we can divide. Of course, you can have sub classifications of all these as well. So, initially what we do, we will be talking about some of the nitrogenous cross linking agents, and we will be working with cellulosic material, right. So, we shall first learn about urea based. You know what is a urea? So, we will look at the urea based cross linking agents, their advantages and their limitations, and initially we will focus on cellulose. And so, any reaction that we are talking about is we are talking of these agents with cellulosic fabrics, right, which are could be cotton or viscose or polynosics or high wet modulus fibers, etc. What is common in them? Their chemistry, and therefore, although crystallinity may be different, in different orientation may be different in different fibers, but the chemistry is common, and which is this chemistry, which as we said before has got many primary hydroxyl groups which will be relatively are more reactive and therefore, will participate in cross link formation. You may appreciate that we may not be interested in using all these hydroxyl groups for cross linking purposes. That will require too much of a chemical and may change the character completely. The chemistry itself will be so different, like we said about the triacetate. There all hydroxyl groups have been replaced by an acetate group, and therefore, the chemistry has changed, and so the physical properties also change. It is a very different fiber. So, we are not going to be interested, we want to bring in some cross links, intermolecular cross links, and so some of the hydroxyl groups will be used for this purpose. So, one of the urea based cross-linking agent is called the DMU. DMU means dimethylol urea. It has got a group reactive group which is called N-methylol group, and it is formed by condensation reactions of formaldehyde and urea. So, urea and formaldehyde condensates finally give us a compound called the DMU. This group is called the N-methylol group. So, reactive. What is urea? Urea is simple compound like this. But when we react with formaldehyde, then what we get? We get another compound which can be now called the DMU or a urea derivative. So, we have now N-methylol groups on both sides. So, it is a bifunctional agent. Two functional groups on one side and the other side. So, if they react, they will be able to form a cross link. How? Let us see. So, cellulose, as we said, has got many hydroxyl groups, and to simplify this, we can denote cellulose as cell OH. It does not mean we are talking about only one hydroxyl group or that cellulose has one hydroxyl group. No, cellulose has many hydroxyl groups. It is just to make the life little simpler in expression. So, at the end of the thing, you will have this DMU which is this compound when it reacts with cellulose under right conditions of cross linking, then we expect something like this to happen, that one hydroxyl group of cellulose molecule may react like this, the other molecule can react on the other side, and so two cellulose molecules or the two hydroxyl groups of two different molecules can react in this manner and form these bonds, which are covalent bonds. So, basically CH2OC, CH2OC, what is this? What type of bonds are these? These are ether linkages. So, ether linkages are formed. So, a DMU, which is dimethylol urea, can react with cellulose to make a crosslink of this type. And once this crosslink has been formed, our principal position, which was there always, that the molecules are there. So, we have made some crosslinks, and hopefully they will be able to help in recovery from the strains that may be because of our bending increasing. So, in some sense we have solved the problem. Every time you do a process, and that is what the engineering is all about. So, you obviously have got a benefit in terms of what you wanted, like the crease recovery will be better, but there can be some limitations. One of the limitation which people complained about was called a fishy odor. Fishy odor. I mean, this, it looks like as if dead fish, if you have passed through them, some kind of a smell you may have noticed, and that is the kind of an odor, which basically is nothing but the smell of formaldehyde. Formaldehyde. So, from where the formaldehyde has come? The formaldehyde was used to make DMU. Well, it has already reacted. Yes, it has reacted. So, as long as it is reacted, the formaldehyde is not free. The fishy odor comes only when the formaldehyde becomes free. So, free formaldehyde will give you a fishy odor. So, from where does the free formaldehyde come? So, every reaction, chemical reaction, is an equilibrium reaction. One, when you react, maybe 99% reacts, 1% may not react. So, that unreacted portion, but that may become a part of the fabric in case you have not taken it off. But fortunately, you may, if you wash the fabric, the free formaldehyde may get removed. But another equilibrium part of it is that every reaction which has happened also, although very strong, can also go through a reverse reaction called hydrolysis. You wash the fabric which has been treated with DMU. So, there is a reverse reaction also is possible. After all, what is bonding? Bonding is a contract. Some better contract called the covalent bond, and the weaker contracts could be hydrogen bond, but there is a contract. So, equilibrium reaction happen. It may hydrolyze, maybe very less, but it can hydrolyze, and when it hydrolyzes, a free formaldehyde can be generated in the washed fabrics, in the stored fabrics, in the fabric which have been kept in a moist condition for a long period. So, when you open it, you see smell. So, people did not like it, that is one part, and so one worries about it. Also, this compound, being a simple linear chain, was found also to self polymerize. Instead of just cross linking with cellulose, it could react with itself and polymerize, and if something like that happens, that means a film kind of a thing may be formed, and if that happens, people observed stiffness. After reaction, the fabric became stiffer compared to when they were not treated, and so these became some of the limitations, and people wanted to do something about it. Another problem with the DMU, now we are talking about DMU, was a chlorine retention problem. sometimes people do their laundering and washing in solutions which may contain chlorine compounds like bleaching powder, hypochlorous compounds, sodium hypochlorite, and if that thing happens, then we have a problem called chlorine retention problem. What is the chlorine retention problem is that if some compounds like this are available, then they may replace this hydrogen, which is called a labile hydrogen, by this chlorine. That means, hydrogen on the nitrogen can be replaced by chlorine atom, because you have had some possibility of any such compounds called the hypochlorites and so on and so forth. So, you say, are we bothered about it? Yeah, we are bothered, not because the chlorine which has been attached. If it attached chlorine, normally it is okay, but if it also can get hydrolyzed in heat and moisture, then the chlorine comes out and it can become HCl. Then HCl can be a problem. I am not sure if you recall that the cellulose by itself has so many ether bonds, and ether bonds are also susceptible to acids. So, acid hydrolysis breakdown happens, and so you can see yellowing, degradation of the fabric also. So, this is your chlorine retention. So, retention and release. So, this is a compound which has got a labile hydrogen on nitrogen, some kind of a hypochlorite compound may come in contact, it can form an NCl type of a replacement, and once that happens and you provide heat and you provide moisture, then this compound can go back to this, but in the form can make another hypochlorite glucose, and which can produce HCl. So, if this happens, then obviously it is not so good. So, these are some of the limitations that we talked about. So, as an engineer, you should always appreciate that you can do one good thing which is very nice, but it can be associated with something else. So, you have to find a solution for that also. You can't just say, well, this is done, nothing more can be done. Therefore, we keep researching, and therefore, there is always an anxiety in researchers as to what can be done further. One of the things which people did, next compound which came into commercial existence, is called the DMEU. What is the difference? Now, you see, this is a compound which is like urea. It's like the carbonyl group is here. So, this is the carbonyl group, this is like an urea group, which is the N-methylol. So, it has got methylol group which can react, but it is a cyclic compound. So, there is this area is the ethylene, additional ethylene has been added, and so it becomes a cyclic compound. So, it is a cyclic urea. So, this compound which is called dimethylol ethylene urea, okay? Dimethylol ethylene urea. So, DMEU. So, ethylene group, as we said, has been introduced to make a cyclic compound. You can always calculate the molecular weight of DMU and molecular weight of DMEU. Obviously, which one is higher? Obviously, DMEU is going to be higher. But what you interestingly see is the nitrogen. This nitrogen has no labile hydrogen, all right. That is an interesting part here, just because you have made a cyclic, no labile hydrogen on nitrogen. So, how does it reacts? Let us see first the reaction. So, one of the advantage could be the chlorine retention, no chlorine retention. If no retention, no release. So, good idea. Let us see how the cross-link will look like. So, we have the cyclic compound DMEU, it can again make an ether link with cellulose and create a cross link. So, it is cyclic, no hydrogen here, and that means no chlorine can be retained and no release, plus once becomes cyclic, the self polymerizing tendency reduces quite a lot. And so, people found that it does not self polymerize, it only cross links. We are interested in formation of cross link, we are not interested in formation of a polymer or self polymerized material, we are not interested. And so, the DMEU gives you this advantage. Any limitation? So, we always look at what is difficulty. One of the things which people would say, after cross linking, what have you done? You have reduced the number of hydroxyl groups available on the cellulose, because those hydroxyl groups have been used to make the cross link. So, you may increase the hydrophobicity. It is not that all the hydroxyl groups are gone, very few hydroxyl groups have gone. We will try to do some calculation at some time to see how many such cross links would be required to give some reasonable amount of crease recovery. But some hydrophobicity is introduced, which can't be denied. So, let us see what have we learned. We have learned why do creases form in fabrics, okay, something to do with the fiber, but we measure in fabrics. What is resiliency? That is, it is resistance to deformation and recovery from the deformation. And how does this resistance to creasing be increased? That is done by cross linking. And so, we have also learnt about cross-linking agents, which type of cross-linking agent will require. We will also have seen that DMU could be an effective cross-linking agent. It has some problem related to fishy odor and chlorine retention and also self polymerization. But if we make it a cyclic urea compound like DMEU, then some of these challenges could be handled, right. So, you can do it yourself, test it yourself, obtain different types of fabrics, check which one creases more. If you can correlate with its chemistry, is very good. Also, see if fabric structure has any role to play in recovery or creasing itself, a knitted structure versus the woven structure versus different kinds of weaves. You may like to see it yourself and maybe come out with some explanation as to why one of them is recovering more than the other or creasing more than the other. So, here we stop and we will meet in the next class. Thank you.